Hi there, this is session 31 of Programming from the Very Basics using Python. In the previous session, I introduced you to generators and I explained how they work with simple examples. I told you how you can use the yield statement in a function and it turns into a generator. And I also explained about the iterator protocol and I told you how you can iterate over various objects using the iterator semantics and what exactly happens inside. I also told you that a generator is merely an implementation of a iterator protocol where values are generated on the fly by the function. So, which means you don't have to wait till the function accumulates all the data into a list or any collection and hand over to the caller, but rather it can yield out dynamically in runtime. In this particular session, we will revisit generators with some more examples and explain more in depth about how they work. I'll also tell you about various built in generators that are available built into Python, and I'll also explain about the yield expressions. Let's get started. In the last session, I talked about creating simple function like the Fibonacci series, which would be implemented as a generator version of it. So here I will show you a couple of more functions and explain how you can do something like multitasking using generators and their limitations and the role of using a coroutine. Now, first of all, let's assume that I have a function here. Let's call this function as, I'll create two functions. Let's call it task1. And inside this function, I'm just going to use for I in a simple counter. I'm just trying to create a simple counter, which is just going to print messages on the screen, nothing more. So I'm just going to type task1 counting I. And let's say I'm going to introduce some delays in here. Let's put a sleep of 1 second. And for this, I might need to import the time module. So let's say from time, import sleep. I'll create an exactly similar function and just call it task2 this time. And every time it runs, it's just going to print task2 counting whatever number. So I'll just call this task2. And now, let's say these two functions are going to be performing two different tasks. And they have some inherent delays where they actually sleep, wake up, and perform some activity. Now, if I run these functions in a sequence like this, you can very much predict what the outcome of this execution will be when I run this. You can see that task 1 alone runs for 10 iterations, as you can see here. After 10 seconds, you can see task 2 starts its work and starts counting numbers. And this is an example where the code is executing sequentially, which means that you first have to finish the first function, which I call as task 1. And when that function completes, then you move over to the second function and try to execute that code. So this is a kind of sequential execution, and most of the time, the program is sleeping. So you can see that it just prints a message, sleeps for 1 second, prints another message, sleeps for another 1 second. So assuming that to print a message, maybe it takes a few hundreds of microseconds, let's assume, or maybe a millisecond or a couple of milliseconds. So you have a few milliseconds of execution, 1 second of sleep, few milliseconds of execution, 1 second of sleep, and that's how the sequence is built up. And you can see that when task 1 is actually sleeping for 1 second, I'm not able to give control to task 2 to do its work. If at all you have a scenario where these two functions or two tasks are not related to each other, you can run them in tandem, that is concurrently. And how do you do that? One of the ways to achieve this is by using generators, which I will show you now, the same code. So right now you can observe this particular function. It's a simple counter, but I say for I in range of 10, I'm printing a message and I'm sleeping here. I'm going to put a sleep function to sleep for 1 second. If you want to transform this into something that can cooperate with others, we also call them as coroutines in real world, in programming that is. But then if you want to transform this to work like a coroutine, I would not call this a coroutine though, but if you want to make it work like a coroutine, the way you can achieve this is before I'm going to block, this basically is a blocking call. This is also called as blocking, which means you're blocking execution for some time, waiting for some event to happen, in this case, a 1 second delay. And after 1 second, you're woken up and you're trying to execute it, execute one more iteration, right? So before I block, I can be nice to others in this code, that is, and give up the CPU. So the other task that's waiting can get an opportunity to run. How do you create a cooperative multitasking between them? I use the word cooperative multitasking. What is a cooperative multitasking? Think about a scenario where there are two tasks. One task is doing some using some resource, that's a CPU in this case. Once it knows that it has to block for some time, which means it does not need to use the CPU, it can give up the CPU so that another task, if it has some job to do, it can utilize the CPU in meanwhile, and then that task can cooperate again by yielding out the CPU to the previous task. And this is how you can actually make them work together, right? It's like this. Let's say you have two workers who are doing some work. Let's say worker one is filling up some activities and performing some activities, and worker two has to wait until worker one completes all of his job and then continue. But if you want to make worker two work in tandem with worker one, when worker one completes small part of the job, worker two can take over, do some small part of his job, then worker one can take over, and this way you can make both workers to work simultaneously. And that's the whole intent of this code. So for all I want to transform this to a generator variant, what I need to do is I can just see that. You can just see that before I call a sleep of 1 second, I'm just going to use yield here. And I'm going to do likewise in this case. Let's say printing a count is a job that this task does. And after it's finished its job, before going to sleep, it's going to yield out the CPU such that another task can actually go inside the loop, print its count, yield out, so that it can go back to task one. And after sleep is completed, maybe task one can continue printing the next count, yield out. Task two can now print the next message, or maybe go to sleep, come back again, print the next message, and then yield out. So you can see that I'm trying to create some kind of multitasking between these two routines, which is there here. Now, when I try to call task one and task two this time, as you can see that you won't see the functions running. The reason, I've told you in the previous session, that the moment you use a yield statement inside a function body, the function is transformed into a generator. Therefore, you need to get the return value of these calls, which are generator objects, and then start kickstarting the generator through a loop, maybe some kind of a for loop. So we'll do this right now. What I'll do is I can directly, rather than running as task one and task two, okay, I'll just copy the cell and I want to show you what this does. So I'll make another copy here, and you can very nicely set up a small scheduler, let's say, right? By using simple for loop, where I can just use maybe, underscore comma underscore. I don't really care about any value being yielded. So you can see both these tasks don't yield any value. They just return out the control. I'm not yielding any count or anything as such. So that's why I'm using two underscores there. In range, or not range, sorry, zip of task one and task two. Closely observe. When I call task one here, it returns a generator. Calling task two returns its own generator. So there are two generators returned. Let's call them as two different tasks, representing that function body. When I use zip, what does zip do? Parallel iteration. Gets one item from the first iterable, gets the first item from the second iterable, the next item, next item. It tries to get elements in parallel from these two iterables which are being passed as a parameter. So the generators are iterables. So obviously task one, task two returns generators, and the zip will take care of coordinating within them, getting things in parallel. And now we can try to print them. I don't have to do any print because nothing is actually done by these tasks. So I can just put pass here. That's sufficient, I guess. So try running this now. You can now see a very interleaved execution. Task 1 counting 0, task 2 counting 0, task 1 counting 1, task 2 counting 1, task 1 counting 2, task 2 counting 2. You can see an interleaved execution here. This is a kind of multitasking. You're not making task 2 wait until task 1 completes. You're trying to make it run alongside as early as you can. But there's a small issue in here. The issue is that the total time taken for task 1 and task 2 to complete should be half, isn't it? I mean, if at all you look at the previous code, when I ran this here, this took about 20 seconds. We can see that. It took 20 seconds to complete. It shows 20 seconds in here. That's the time taken. I'll rerun this. Task 1 takes about 10 seconds to complete because there are 10 iterations and 10 times is going to call sleep of 1. It's not considering the time taken by print, which is very minute. But you can see completes in 20 seconds. You can see this counter. The moment it hits 20, that's where the program completes. So this is what you see here. But by making them run together, right, in tandem, I was expecting this to finish in half the time, right? You should finish in 10 seconds. But unfortunately, if you run this, maybe you get 1 second improvement. It finishes 19 seconds perhaps, but you can see that. Though these tasks seem to run concurrently, the problem is that it is spilled beyond 10 seconds. In fact, I was expecting it to finish in half the time, but it took about 19 seconds in here. To understand why this happens, I need to explain it with a small graph to show you how the execution sequence is. So I have drawn up a small diagram in here. I think I have it here. Yes. A very small diagram. I just pre-draw it so I don't have to waste time in my video. So just consider this particular block representing the CPU time used in executing task 1. And this particular block represents task 1 sleeping. That's function 1 sleeping. And this particular block represents having the green color block that you see here is nothing but task 2 running and this task 2 sleeping. When you run them sequentially as normal functions, first you can see that task 1 runs, sleeps, runs, sleeps, runs, sleeps on its own. Once it's completely finished, then control goes to task 2, which is the second function, and that does its job sequentially. This is what happened when you ran the code without using yield statements. This is sequential execution. But when I use yield, we saw an interleaved kind of an execution. But if you see how it worked, it's like this. You can see that task 1 executed. It printed a message. After printing a message, like counting 0, it did a yield, like you can see here. So task 1 went inside a for loop. It said, task 1 counting I, then it yielded out. The moment it yielded out, basically the for loop, right? The for loop is having 2 generators. When it yields out, the zip will try to call next of task 2, right? Next of task 2, which is the generator for task 2. And task 2 takes control and starts executing, printing its message, and this yields out. The moment this yields out, nothing happens in the for loop. The for loop body is blank, right now. But maybe you can put a print statement to say that even the main code is running alongside. It's fine. So after which, when task 2 yields, the next iteration, again you call next of task 1. After yield, the next statement is sleep. You can see task 1 blocks the CPU. And then after sleeping for 1 second, it goes back in here, prints the next count, it's 1, then yields out. The moment it yields out, now control goes to task 2. Task 2 continues to sleep because task 2 had yielded earlier here. It continues to sleep for 1 second. Then task 2 goes back to the loop, prints counting 1, and then yields out. And the cycle repeats. And if you look at in a graph form, this would be task 1 printing a message count, printing count 0. Then task 2 prints count 0. Then when task 2 yields, it goes back to task 1 where the next statement is sleep of 1 second. After sleeping for 1 second, it goes back to the next iteration in the loop where it actually prints task 1 counting 1. Then it yields out. When it yields out, the next statement in task 2 is supposed to be sleep of 1 second. Then it wakes up again when it goes into a loop. And then task 2 prints counting 1. Then it yields, goes back to task 1. So you can see the sleeps are happening in a sequence. That means task 1 takes 1 second to sleep. But again, task 2 takes another 1 second to sleep. So they get added up. So the total time taken is still the same. Just that instead of waiting all the way till task 1 completes and then running task 2, you're able to interleave this execution. And this is what happened when I used the generators that is there here, right? Maybe we can do one more thing is to visualize this. We can also take this entire code and trying it in pythontutor.com. I have told you about pythontutor.com. If you want to visualize a lot of code, you can actually go ahead and do it here. When you click on start coding in Python now, and this code is not really using any special features, so I can actually maybe I'll anyway select 3.11, no harm in it. I'll paste this code right away here, and let me try to visualize execution. And okay, I need to reduce the font size. Oh, time not found or not supported, one of these modules, blah 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 blah. I think time module is not supported, so I think we need to unfortunately, I don't think you can use time and sleep, but it's okay. We'll just comment this code off. Python tutor could be a little limited because they don't give you all the functionality in here for security reasons, perhaps. So I'm going to comment off these lines that has sleeps for now and try to revisualize the execution. You can see there are two tasks here, task 1 and task 2, right? Two tasks that are there here. And you can see that when I use it shows yield here. Okay, I'm not sure why it went. Oh, okay, it went to so many steps. Let me go back to the first step. This is def task 1. When I go one step forward, let me just reduce the font size. Perhaps I can get access to much of the screen space, or let me zoom this up a bit. Yeah. Now click on next. You can see task 1 is defined as a function. Next. Task 2 is now defined as a function. The moment I say next here, zip goes inside task 1 and it goes inside the for loop. It prints this message. You can see this. It prints this message, task 1 counting 0, and then it yields out. The moment it yields out, it goes back to task 2. Zip will call next of this generator, and then it control goes to task 2, goes inside the loop, prints a message, task 2 counting 0. Then task 2 yields out. It goes back to task 1. It goes into the for loop and then go to next iteration of for loop. It goes inside the task 1's next. You can see a task 1 continues where it had earlier left off. It had left off at yield. After yield, it has to call a sleep, but I just committed a sleep. But assuming the sleep finishes, then task 1 will go back to the for loop, and then it prints the next message, count 1, yields out. Now you can see that it goes back to task 2 because zip will call next or task 2 after that, and this will call yield. And again, you can see that it goes inside the for loop. It's after yield, right? It goes into the for loop, and then it prints the next message, yields out. You can see how the control is flowing through both of these code parts in two different routines I've created here. I wouldn't call this a function because functions are run to completion. So I'll call a generic term called routine. It's like a subroutine or a coroutine, right? So it's a separate procedure, but it's not like something that you run to completion and take control, right? You're switching control between these two routines that is there. In fact, these are called as coroutines in programming world, but I would not term this as a true coroutine because you look at true coroutines that are available. The sleeps, if you use a sleep in both of them, you don't want the sleep to interleave. So how a timeline of a true coroutine would look like, it has to look like this, which will take lesser time. You can see the timeline. This is stretched out. And so is this, right? This take almost like 10 seconds, let's say, this particular end. But when you look at the actual coroutine, would almost finish in half the time. Almost. How does it work? You would want to expect task 1 to run, then pass on control to task 2. Then when task 1 is sleeping and task 2 is sleeping, you want to make sure that sleeps are together. The sleeps happen together. And then task 1 wakes up, gets to execute. Task 2 is transfer control to task 2. Task 2 executes, and they both sleep at the same time. Rather than interleaving the sleeps. You want to make the sleeps happen at the same time. This way, you can actually implement better concurrency, right? So you don't want to wait for every single blocking activity for every single coroutines in here. So that's exactly how coroutines are implemented. In fact, you cannot really do it purely within programming logic. In order to implement this as a true coroutine, you need to get help of the underlying operating system. Most operating systems today, all the popular operating systems, have some kind of uh, poll mechanism and poll and event poll kind of mechanism. We call them select system call in Unix, and there are also poll system calls in later variants of Unix. There is a kpoll API in macOS and FreeBSD, let's say today, and also in Solaris. And Linux has got something called epoll. I guess on Windows, I'm not sure if it's called as IO completion, whatever it's called as a terminology. But it's all of them work on the same principle. I'll tell you a more realistic use case like this, where it is used. Let's assume I'm building a web server, some kind of an application. So maybe let's take a web server as an example. We all communicate on the internet using web browser, which goes and hits some web server and then fetches in data. Now, when I send a request to a web server, let's say I make a connection. When I send a request to a web server, immediately for the request, a response is sent by the server to the client. Now, let's say I pull in a web page. Now, when I'm reading this web page, I'm not sending any more requests to the server. As one client, I'm not sending any requests to a server. So I'm actually reading it. As a human being, I'm just reading it. It's read in my client. And now when I go and click on a link on a web page, another request is sent. And then that request is processed and I get back a response. Then there's a long delay in which where I'm trying to process that response here on the client side. But I might be reading, I might be interacting with it purely in the client side. And when I hit some other link or some other entity or any widgets on a web page, only then a request is being sent, right? So if you look at the way the request response works between a client and a server, especially for an example of a web server, client sends a request, server quickly responds, and server is now waiting for the next request for a long time. Then I send a next request, server responds, then there's another wait. While the server is waiting for my next request, you don't want to keep the server hooked on to one client alone. That's me. Obviously, on a typical website, you'll have hundreds or even thousands or even close to 100,000 clients connecting at a given time. It depends on the scale of the web server, right? So if you look at search engines or stuff like that, which has got the most heaviest traffic, everybody is hitting Google or DuckDuckGo or any of the search engines, right? Or Bing. So they go to search and they're searching it. When I give a search, the search engine does its magic, gets all the search results. So the response is sent. Now it shouldn't be just waiting for this client while you can process another client. A realistic example is how some busy places like restaurants take order. Imagine you have a very small restaurant where you have very few employees. Maybe you have a single waiter, many tables. The waiter goes to the first table and says, "What do you want?" And you say, "I want a coffee." And he says, "Not it down," and goes next table. "What do you want?" "I want this. I want this." So he's like polling for events from everyone, right? Polling for events for everyone. Okay, do you want anything else? Do you want anything else? Do you want anything else? Okay, I note it down what I want, and I place on the request. This is also called as an IO reactor model. IO reactor. That means you're trying to get input and then channel out the input to the backend, then give an immediate output if it's available, then go to the next one, go to the next one. So you're keeping yourself busy polling for activities so you don't make a client wait. When I'm busy with one client, let's assume that I've seen some scenarios where I go to some place, like say these kind of eat out restaurants, eat out kind of outlets, I would say rather. Let's say I go to a cafe shop, it's an eat out kind of a cafe shop, and there's a queue. Many people are standing in the queue to place their order. Many times there's a person who is taking the order, he's just trying to note down what the order is. When you go out to this kind of when you go to this outlet, maybe there's a person standing in front. Let's say it's me standing in front, and now I decide what I want to buy. I look at the counter there and say, it can be frustrating to people standing behind me because I'm taking a lot of time. I couldn't make up my mind. So I keep querying that person and saying, do you have this? Do you have that? No. You want to make sure that the entire thing is efficient. So when I'm busy looking at the menu, okay, this might not look very polite, but maybe the person at the counter might actually look at me and say, oh, this guy's taking time. Your next order, please. He's going to pass on to the next person because this person is busy. I'm busy thinking what to order by looking at all the menus being shown up there, right? Maybe they put up menus on the outlet, right? Which is like on the board. So you look at the menu board and just trying to decide what I want to buy. Person behind me is now wanting to place an order. So you try to channel out the control to the second person, say, are you ready? You have an order? Okay. The person says, and yes, okay. Place the order. Then I make up my mind and say, I want this. So you can see how rather than processing things sequentially, you're trying to make sure that anyone who's got an event immediately, any member who's got an event, you know, process that event quickly and keep polling for events across the board for multiple listeners or multiple subscribers, you could say, right? Multiple clients in this case, if it's a web server. This is exactly how most modern web application servers are being built. They have an event loop. We call them an event loop. This IO reactor model is also called as an event loop. So you're constantly polling for events, constantly polling for events. That's done by the operating system. You tell the operating system, if this event occurs, let me know. If this event occurs, let me know. If this event occurs, let me know. You put on a lot of list of events in a queue. The operating system will do all the kind of polling. There are some internal interesting algorithms to use that's being done in different OSs. But it's also called as multiplexing the operation. It's also called multiplexing, right? Instead of doing things sequentially, you multiplex them. This is how we do multitasking in real world, don't we? Let's say I just ordered something online and for delivery at my home. Maybe I just ordered some snacks to be delivered. It's going to take some time, obviously. So while the snacks are going to be is on delivery and the delivery person searching my place and is on the way, is en route, I am free. I can be watching some channels on my YouTube, or maybe I can be doing something else, maybe reading a book. So I can keep myself busy doing something else when I place an order and the order is yet to arrive. And when the order arrives, I switch control to that and I process it. Maybe I get the snacks from the delivery person and I would actually have it. So this is how we do multitasking, right? When you have a lot of tasks at hand, you sometimes want to finish most of the tasks together. So what do? You channel out your time for one task. Then after a while, when this task is ongoing, I can take my time off and do something else. This happens in development also. Let's say I start a build. I start a build on my system. Builds can take a long time. I'm building some big software. Maybe I'm building an Android or a Linux kernel or building Python from source code. So if I'm doing something like that, the builds can take some time. Or maybe I'm installing new software, a big software. It's going to take some time. While installation is going on, I'd like to put my attention on some other application, look at that, and maybe that application also puts a delay. Maybe I try to initiate a download while the build is going on. I initiate a download for a big file on the internet, and I'm downloading that file. The download is going to take some time. I'll open up a new tab, do something else. Yeah, the operating system is working alongside with me to help me in multitasking. But what I'm doing here is switching between multiple tasks, right? This kind of multitasking is what coroutines let you perform. Now, there are many ways to achieve multitasking. That's a big topic. I'll be covering in depth in a specific training of which I'll do on training videos, which I'll do on, concurrency and parallelism. But now there are three different ways that Python lets you achieve multitasking. The first one is using coroutines. Coroutines are used when you're having some kind of an event loop where you're mostly waiting, mostly blocking, right, for events to occur. And when events occur, the time taken to process those events are minute amount of time, like this loop which I showed you. You just print a message, then you're going to sleep for a long time. So the sleep times are longer, the wait times are longer, the execution times are extremely short. The ratio of the wait versus execution, or the execution versus wait rather, is also called as a duty cycle, right, of your process, your CPU execution. So it's a ratio. If your duty cycle is very, very minimal, let's say you're executing, like, say, for 10 milliseconds and sleeping for an average of, like, say, 1 second, executing for 10 milliseconds and sleeping for 1 second. When this process is sleeping for 1 second, if there are many other events like this waiting on queue, you can process them instead, right? So this is a benefit that you get when you're using coroutines. In summary, if at all you're trying to build products or projects which work on a lot of IO requests, mostly IO, and this IO request responses are, having long delays, using coroutines makes sense, right? If you look at all these event loop algorithms, are nothing but just implementation of coroutines in different languages or different frameworks, right? They do it in different style. In Python, we have coroutine frameworks now. Earlier, we need to depend on third-party library to get support for coroutines like these. I remember back in the days where there was a sophisticated framework called Twisted Matrix, which is quite popular though in the Python 2 world. That's back in 2004-5 time frame when that project was released. It was quite popular. I think it's around that time, right? And in the later years, there were many other frameworks which aim to be more simpler in API, are more lightweight, is more is more Pythonic and maybe more simplistic for us to use it. One of them I can think of is eventlets, and then there is something called G event, which is my personal favorite even today. So all of these libraries or frameworks let you build coroutines. But since Python 3.2 onwards, the Python community, the Python developers, the Python Software Foundation rather, the community of the Pythonistas who are contributing to Python, they started looking at implementing this as a part of the standard library. And it has been evolving. Initially, we had some decorator syntax, which is another topic which I'll discuss in a later time. And they implemented async IO decorators, and they came out with the standard library called async IO, which lets you implement coroutines in Python standard library itself without looking out for third-party libraries. It evolved over time, matured over time, and by Python 3.6, they introduced a new keyword called async and await keywords to implement coroutines. And since Python 3.6, there's been a little more refinement, I guess. In Python 3.7, the API has been further refined to make it more simpler and more accessible. And a couple of libraries which deal with networking mainly, or most of these IO libraries, which I would say, they were transformed to use async IO. There are async IO variants of those libraries available. So that's how you see async IO. I will just give you a simple example show you a simple example of how to use async IO as an example here to show you how coroutines work, and I'll come back to generators. So if you want to write a coroutine here, which is the coroutines today, you don't use this yield and all these semantics. And unfortunately, I don't think I can use coroutines in a Jupyter notebook. The Jupyter notebook itself runs a big event loop. It runs an event loop to handle a lot of events. So you cannot launch your own event loop inside Jupyter notebook. It throws a warning. It doesn't work as well. So if you want to try out code with coroutines which implement async IO features, it's better you do it in a separate .py file. So I'll show you how it is done in a very basic form. I will cover in depth about it when I talk about concurrency and parallelism. So today coroutines are one of them. I had to finish that first. Coroutines are one form of multitasking. There are also something called threads. Threads is another form, right? So threads is another way of doing multitasking. We call them as multi-threading. Threading is more of an architectural pattern, though there are different implementation styles for it. So we have a lot of plethora of threading models and implementations that evolved over time. Primarily, I would say that threads are nothing but you're creating a simulation, the programmer, that there are two program counters or more program counters. So rather than you having one single control that's going instruction, you can create another thread of control which you can make it point elsewhere and start executing them. So there's multiple threads of execution in the same code base. So normally what you do is that you will have one function which you spin off in a separate thread of execution, your another function that you can spin off in a separate thread of execution and make them work in tandem. And in all the modern operating systems, which are multi-threading capable, which includes Windows and Mac OS and Linux, most of the threading libraries that you find in high-level languages, including Python. Python also has a threading module. it abstracts or provides an interface to the operating system threading interface. So, how the threads are implemented, how they work, their APIs differ from one OS to another, right? So, though in the Unix world, it's very common to use the POSIX threading library, which is a standardization, though the implementation could be different in Linux and Mac OS and FreeBSD and so on. Windows has its own Win32 threads, and I'm not sure if it's called Windows threading libraries, which might have a different kind of an API feel to it. So what they've done in Python is that they provided a very simple abstract interface which hides the operating system's implementation. So I can write a multi-threaded application on Windows, and the same application can be easily run on Linux or a Mac OS with not much of changes, right? And multi-threading, when I say that, it's now an operating system feature. And where would you use threads? One of the primary uses for threading, I would say, is for managing your graphical user interface. That's the original intent of having threads in operating systems, right? Mostly for GUI. When you look at graphical user interface. When you look at this graphical user interface, there are a lot of widgets in here. There are a lot of widgets. A lot of buttons and widgets. When I click on this button, I want certain activity to happen. When I click on this particular menu, I want some other activity to happen. When I scroll this window, I want this window part must alone be updated. So you can see that there are a lot of things going on. Or maybe I can have multiple widgets that must be updated together, right? So it's for example, let's say if you're using Windows, if you use the Windows Task Manager, as a classic example, you'll see a lot of graphs coming in. Or maybe you have Activity Monitor on macOS. So you see a lot of these graphs and multiple graphs coming up. Or maybe on my Linux system, do I have anything like that? Maybe I have to look at the GNOME System Monitor. This is not my regular desktop. That's a sad fact. OBS Studio seems to work very well on this, but my Arch Linux is mostly command line. So let me run GNOME System Monitor. Yeah, it came up in here. This is an example of a use case of multi-threading where you can see multiple graphs are getting updated simultaneously. So you'll have a separate thread that's updating this, separate thread that's updating this, another thread is updating this, and maybe a couple of threads which are updating these items. It can be done with threads, but it can also be done without threads. Okay, so having threads of execution gives you a better abstraction to perform multiple tasks simultaneously, rather than having a giant event loop where you poll every single activity. So it was meant mostly for this. But over time, I guess in the 2000 era especially, threads were used as the primary means of multitasking in many frameworks. And there are some languages like Java that only provide threads as a means of doing multitasking for a long, long time. So threads were quite commonly used for even building web applications, web servers, handling multiple clients requests and everything as such. But there are a lot of scalability issues when it comes to threads, which has got to do with the limitations of the operating system. Most OSs have some limitations on how many threads they can manage at a given point in time on behalf of a process. Because every thread that you create will allocate some resource in the underlying operating system. So there are some limitations that most OSs do impose. And threads, which used to be called lightweight, is not that lightweight anymore compared to coroutines. When you build a coroutine, you're not trying to take any help from the operating system apart from the event loop. Most of your tasks or abstraction of tasks and switching between them is all done by the library in the language, right? So only polling for events is done by the operating system, but context switching between tasks is all done at the application tier. That's one benefit that you might get, but there are drawbacks. If at all I have a coroutine that takes more CPU cycles and doesn't yield out a CPU, it might starve out all other coroutines. Coroutines are designed to work in a scenario where you want to do something like cooperative multitasking. Threads, on the other hand, especially operating system managed threads, which is the norm today, are preemptive by nature. So when I create a thread, I don't really know whether the thread will take continuous CPU cycles or whether it's going to block. I don't really care. I just create a thread off. The operating system will try to preempt that thread if at all it goes beyond a time slice to make sure other threads get an opportunity to run. So it uses preemptive multitasking. So that is the principle in which threads work. And then at the final form of multitasking is parallel processing, where you create separate processes that can work in parallel. Each of them will have their own view of resources. Threads and coroutines share all the resources, right? Threads might have their own stack. They can maintain their own local state, but they share all of the memory, the heap, and everything else is shared. They only have a view of their own CPU. Only CPU is virtualized. Every thread is made to believe that it's got its own share of CPU that can execute, but they have to share the same memory, share all of the resources in an application. Coroutines are pretty much the same, just that there's no preemption. Coroutines have to give up the CPU on their own. That's what they are, right? Coroutines are also called as green threads, greenlets, and all these terms by other languages, other environments, right? But they all mean the same. It's also called as the user level threading sometimes. They're also abstracted that way. However, if you look at processes on the other hand, they live in a completely virtual world. They have their own virtualized memory. They have their own virtualized CPU in all the modern operating systems. And one process will not be able to mess around with the other without the operating system's intervention. So, for example, this is one process, this is another process, and this VS Code runs in a separate process, and they're all running independently. They don't know each other. They can't communicate directly with each other. They have to go through the operating system to communicate. The OS acts like a broker to communicate between these processes. We call them as IPCs, interprocess communication mechanism that OSs provide. The point is that when you run multiple processes, each process can run simultaneously in parallel. Can threads run in parallel? You can run threads in parallel in multi-CPU architecture, but there are inherent limitations that you take care of, mostly to deal with synchronization when they're sharing common data, right? It's like this. When you have two threads running simultaneously, it's like two people sharing a room. You know, there are a lot of resources that are being shared in a room. Imagine you live as a bachelor. Sometimes you share your room with your friends. This happens when you go to other companies or any other locations from your hometown and work or study. You have had that experience where if I'm using the restroom, obviously my roommate cannot use it. It's a lock, right? It's a locking mechanism. You have to wait, or you have to wait until I'm done. That's the way it is, right? You have to sort of synchronize between the resources that you share, right? That's how it is with threads. Running multiple processes is like each one get their own room with their own restroom and everything completely. It's like private. I have my own private space, right? I have my own private space. And my friend has his own private space, let's say, in a separate room. No disturbance. So there's no contention on resources. And that's how processes are designed to work. There are certain resources that processes do share, which are operating some resources, like devices, for example. Most devices are being managed. That's where operating some features are used to manage contention, right? That's where IPCs are used, right? If at all you want to synchronize amongst processes. But that's a very rare scenario. Mostly the data that is there within a process address space is completely separate from each other, right? I will go much detail into it, more elaborate in another series of videos. I just gave you a very high level understanding on three forms of multitasking: coroutines, threads, and processes. Use coroutines for purely IO oriented kind of events where you want to handle massive number of events which are IO bound. Coroutines are preferable, and they work on a principle of cooperative multitasking, which means that the execution, right, of your CPU utilization must be as minimal as possible. You get a request, you process the response, and you go to sleep for most of the time. That's how this code must be. And that's a kind of candidate that is well suited for coroutines. They have to give up the CPU periodically to play nice with others, right? Threading is used to do multitasking in a preemptive manner. GUI is an example. When you run a GUI, these GUIs are not always IO intensive. This could be quite resource intensive on its own. There's GNOME System Monitor. It's an INI because you use that tool to monitor other resources, but this itself takes up a lot of CPU. This tool takes up more CPU. You see who's taking up most of CPU right now? You can see GNOME resource monitor should be on the top. Okay, actually, OBS Studio and everything is on top first. But I see resource monitor does take up some amount of, yeah, I can see this, it's on here. It is taking its own CPU. You can see this, its own CPU and memory and all that. Yeah. The point is because this got multiple threads and these threads would be competing with each other for the share of CPU. They might be CPU bound. They might toggle between CPU bound and IO bound kind of activity. And they are best run in a preemptive manner. You give some time slice for one thread. After a time slice, you take the control, give it to another thread, take the control back, give it another thread. So threads don't have to worry about yielding out. Right? That's the whole point of multi-threading. Parallel, when you say multiprocessing, they use it for running multiple processes which run in their own virtual address space, and they can run truly in parallel in multi-CPU kind of architecture, as long as they don't contend on operating system resources like devices and other resources other than memory. Any other resources, they will generally have some contention. So that's the only part you should take care of. So these are the three levels of multitasking, and coroutines are the very basic form that you can fully model in a programming language like Python here. So if at all I want to show you how a coroutine can be written, a very basic way to do that is I'm going to create a file. I'm using async IO features, which is available from Python 3.6, but I'm going to use 3.7 kind of syntax, which is much more simpler. So I can just start with import async IO. You'll need this library for setting up sleeps. And this time to define a coroutine, you type async def and you type a function name. Let's say task 1. And let's say in task 1, I have a loop for I in range of 10. And maybe I want to print task 1 counting. And I'll type I. But this time, I can't use sleep in time.sleep. Time.sleep is not async aware, which means that when I do a sleep, I need to sleep and give up the CPU. In order to do that, I use await async io.sleep instead. Yeah, these are some of these changes your code will go through. Await is a new keyword introduced in Python 3.6 along with async. And this is similar to yield. You give up the CPU while I sleep for 1 second. After 1 second, at the earliest, give me control so I can run. That's what I'm trying to hint to the underlying language runtime. And then I can also create another function like this, similar to this, and call it task 2. You can also create a same function called task and take an argument and print that argument as task 1 and task 2. You can do that. I'm just keeping as two different functions. It's all the same, right? They're doing the same thing. You can have the same function run as two different tasks if you want to, passing different parameters. And in the main boilerplate, you'll need the main boilerplate in this. Here type async IO dot run of main. And you might ask me what is main? Main would be another coroutine, which is like a boss thread. It's like a boss which is going to await on both these coroutines to complete. So I'll just type here await async IO dot. It's called is it called run? Okay. The APIs are constantly changing, and I don't write these basic programs anymore. I'll show you from the Python standard library. It's pretty straightforward. All of these are available in the Python library reference. We just look up the code here. Let's try async IO. You can see it shows asynchronous IO. Yeah, you say you call main here, and it's is normally used run until complete, but I think it's called this is what you do. Hang on one moment, please. I think there was a simpler example earlier, but I think they sort of changed it. Is it called wait until complete? Wait a minute. I think there are a lot of these APIs are constantly being improvised upon, so they keep changing. So yeah, I think this is what I should be looking at. Yeah, it's called async gather now. You just have to use that. You say await async gather of task one and task two. The main code you'll call what async gather does is it tries to launch coroutines which you pass as argument and wait until each coroutine is complete. And it tries to run them in tandem. So when this coroutine is calling an await on async sleep, control is going to go to this coroutine, execute it. When this calls also calls await async sleep, it's not the sleeps are going to be concurrent. After 1 second sleep of both the coroutines, each will take turns to execute simultaneously. So the graph when I show you, it's more on these lines when I show you. Task one runs, task two runs, task one and task two are going to call sleep. Then task one gets to run. Then when it awaits, task two runs. When task two awaits, task one and task two sleeps happen simultaneously. So that's how they finish quick. So this is a simple boilerplate example I created. I'll just save this file. Yeah. We call this as async IO simple. I'm not sure why all of these are highlighted. So missing function, doc string. Okay. So yeah, I'm not put any doc strings here, so it's highlighting because of that. So never mind. You can see both of these tasks are sleeping at the same time and waking up almost at the same time and executing. So the time taken over here, rather than 19 or 20 seconds, which it was for the earlier tasks, earlier examples I showed you with even with coroutines, right? You can see the time taken in here. I'm going to use a time command on my Unix environment. I'm not sure if there's a way to do that in Windows. In Unix, you can use a time command. Most Unix shells support it. Linux here will tell you total time taken by this task to complete. You can see it finished in 10 seconds rather than 20 seconds or 19 seconds like it did earlier, right? Because the sleeps are not made sequential, sleeps happen simultaneously. When task one says, wake me up after 1 second, then control goes to task two also says, wake me up after 1 second. After 1 second, both tasks are woken up one after another simultaneously. It's not like task one goes to sleep, then control goes to task two goes to sleep. They're not made sequential. The sleeps happen together, right? Like I showed you in this kind of a diagram compared to what it was when I created yield semantics here. The sleeps happen one after another. You can see this, right? The sleep here, the sleep here, the sleep here, the sleep here. It's like sequential. But here the sleeps are merged to happen at the same time because both of these coroutines are added in event loop. Both tasks are woken up after 1 second, one after another. So task one is woken up after 1 second. After task two runs, then both of them sleep. Task one is woken up to execute. Task two also is woken up to execute. Then both of them sleep. So therefore, you will be able to finish your overall code in much lesser time. If you're like say about you have hundreds of coroutines created, and each of them take 1 or 2 millisecond for execution, but they sleep for 1 second or so on average, the total time taken would be the same in this case compared to using yield semantics, right? So this is what I should know when it comes to what coroutines are at the very basics. So it's just a basic example. There are more examples I will be covering in the further training sessions when I talk about concurrency and parallelism. I'm more of a G-event user. So if you ask me whether I use async IO on a day-to-day basis, no, I stumble on it. I look at existing code that use async IO, that's it. But I have not written any code from scratch using async IO other than writing basic programs for training. G-event has been more convenient. We'll talk about that in another session. Anyways, so the next thing I should talk about is what we call as yield expression. So before I talk about yield expression, I'll leave it at the last. But one thing I should tell you is that generators are there within Python to a large extent. The zip itself is a generator. Remember the zip function, which will try to let you do parallel iteration. When you say zip of, let's type, when I say users is equal to John, Sam, Jones, and places equals, let's try maybe Sydney, Melbourne, and Perth. When you do something like this, when you say for, can say u comma p in zip of users comma places, I was able to parallelly iterate over both of these collections. The core that makes it work, the core part of this code that makes it work is a zip construct. I told you zip is not a function, it creates a zip object. So what exactly is zip object? If you look at zip of users comma places, this returns an iterable, right? This actually implements a generator pattern because when you ask, give me the next item from the zip object, it gets the first item of users, first item of places, and gives it as a tuple. That's about it. It does not create any collection. It just gives it to you on demand. So when you say next of Z one more time, it's going to take the next item of users, next item of places. So most of these constructs, zip, reversed, enumerate, are all built-in generators. They're all generator variants. They don't return a list of tuples or any of such collection. They don't populate no collection. They generate values dynamically. So they implement a generator pattern, right? Just like the generators we created manually. There's also another feature I should talk about is the generator comprehension. So what is this? If you remember, I told you can use list comprehension by using this. I just say maybe A is equal to some numbers, some random numbers like this. When I use square bracket and say V into V for V in A, what really happens is a new list is created using a comprehension expression based on an existing list. You can see that it prints value into value. There's 1 into 1. For 1 in A, first it's 1, then 3, you get 9. For 5, you get 25. So the resultant is a list that you see here. It's shown in square brackets, so obviously it's a list. If you want a tuple instead of a list, what do you normally do? Use a tuple constructor like this. You get a tuple. You might wonder why they used a constructor expression for a tuple, let's say tuple of, but for list, set, and dictionary, you could use them like in literal notation, right? Let's try and find out what happens when I simply use parentheses here. And what you get here is a generator object. This is also called as generator comprehension. Generator comprehension. And this is also called as a lazy comprehension. What it really means is when you actually run this code, okay, I'll just delete this off for now. I say G is equal to, as a generator comprehension, this G is a generator object, just like how I created with yield, right? Python creates it. When you use parentheses and use a comprehension expression. You can also use the filter by using if clause alongside with it. So it's a type of G here. You can see that generator object, class generator. Now what this means is that it does not really pre-compute all these values. It does not pre-compute it. Rather what it does is the moment you try to iterate over this generator object, it's going to compute the square of 1, square of 3, square of 5. That means this expression is evaluated based on you iterating over this generator using a for loop. The more apt way to show you this is rather than calling V into V, right? Let me do one thing. Let me just copy this cell off to show you what it does. Here I'll create a slow square function. Square function that takes some time to find out the square of a number, right? The slow square of V. And this will have a, I'll use, from time import sleep, and I'll put a sleep of 1 second, and then return v into v. Let's say this is what it does. Now I'll show you the result of it. If not, I try to say print square of a, squares of it. Let's say squares of a is equal to, right? Um, Here I will just use list comprehension, and I'll use square bracket, and I'll use v into, okay, I'll use slow square this time, not v into v. I'll call that function slow square of n for n in a. And then I'll also use generator comprehension in here. You can see for this list, it actually took 1, 2, 3, 4, 5, 6 seconds. 6 seconds before it could print this message. Why? Because this slow square is called 6 times for this list. But when try it out for generator, it will not take any time. You can see that. I'll run this cell separately, and I'll run all these cells separately. Okay, so here I've created this function, and here I'll try to call squares of a is equal to slow square of n for n in a, but it's in a list, so it uses list comprehension. When you try running this, you can see it'll take about 6 seconds because there are 6 items in a. You see the result, right? We can also do one thing. We can print a message here. Slow square. Just say invoking, invoked, slow square of, let's use v here. Every time the slow square is called, it's going to print a message, and after 1 second and print the result, right? So I'll redefine this function this way, and then run this cell. You can see the slow square function does its job, creates a list, returns it, and then the list is printed here. But when run it with generator comprehension, just observe, I'm using parentheses here. Just observe whether slow square is ever called. It's not. It just returns the generator object. It's like a lazy worker or a servant. I tell the worker, do this work. The worker says, yeah, done. But when I ask the worker, okay, show me the result, that's where he's going to do the job. Have you finished these tasks? Done. Show me what you've done. Then he said, oh, okay, hang on a moment. I'm going to just do the task. Which one you want? This task, task 2, task 3? So he's going to do it on fly. So this actually works on the fly the moment you try to iterate over it. So it returns the generator objects. But now let's assume that I'll get the generator object one time like this. G is equal to this generator object. So now say for v in G, if I try to print v, now is the time we can see that the actual work happens. Let's say square of v is, oh, okay, it's fine. Squares are. I'll just print v. I could use enumerate, but you can see what's happening. Every time the for loop is asking for the next item from the generator, that's when this comprehension expression is doing its job one at a time. That means this comprehension works dynamically as you iterate over it. You might ask me what's the benefit of it? See, this does not create a list. Imagine I have about 10 million element records. 10 million element records in a collection. I want to process each of those records. So each of the records using some expression. I can use a comprehension, list comprehension, do that to map all the elements to something. Maybe convert all the lines to uppercase, let's assume. Maybe I have 10 million lines of strings and I'll convert all of them to uppercase. One option is I can scan the entire collection and convert each line to uppercase and have another collection. But from the final collection, I want to just get first three elements. Who knows? The code say out of that list, I want just three elements. Then the entire 10 million elements that you computed is wasted, right? But when you use generator comprehension, it tries to pre-create an expression and keep it ready. The moment you try to look out for the result, that's the time it goes and does a job of converting to uppercase as much as you need. And that is the benefit of using generator comprehension over list comprehension. Remember, this is a generator object. It's not a collection. So you cannot do a len and other things in it. So only you can iterate over it. You cannot compute, you cannot find out how many elements are there. That's one limitation. You cannot replace generators in places where a list or tuples are expected if those expressions are expecting it to be a collection. They look for length or in operator, then this may not benefit, right? So it's used in scenarios where you want to iterate over a smaller part of a result out of a comprehension. Then you find this more beneficial, more useful. I just told you all this syntax, grammar, and everything as such. When I talk about file IO, that will be the next topic, I believe. Another two sessions when I'll go to file IO. And now when I talk about file IO, you'll see all these things would be playing together. We'll be utilizing all these algorithms there, right? I will cover yield expressions in the next video. I think we spilled over an hour already. So I think next video I'll talk about yield expressions and odds and ends related to, generators and built-in functions, right? I'll talk about that. So in the next session as such. So I hope you found this particular video useful, where I mostly focused on telling you how generators work. And I detoured a bit. I told you how we can do multitasking in using generators, but I told you the limitations when you do multitasking using generators and how coroutines are actually different than generators, how they use an event loop such that if at all multiple tasks are waiting for an event, they're made to wait together rather than making them wait sequentially. And that's a benefit that you get when you're trying to do event handling or event polling kind of mechanism. I also give you a very high level insight on what threads and processes are. I didn't show you any code samples in this. I want to do that in another video, but then I just give you the gist about how you can achieve multitasking using all this code, mostly concurrent programming code, right? So with this said, I will end this video here. If you have any further questions or queries related to the concepts I'm covering, please feel free to post them in comments. I will answer them when I have time. And if you do like the video, do hit the like button. And if you're already not subscribed, please subscribe so you can actually watch more videos from me like this. So I'll be making more videos, right? So you can watch them. So with this said, thank you very much. So hope to meet you in the next one.